Hello everyone, my name is Ling. Today I will present our paper Leveraging Approximate Symbolic Models for Reinforcement Learning via Skill Diversity. This is a joint work with Sharad and Dr. Rao. In this paper, we provide a solution for leveraging imprecise and incomplete symbolic models to guide reinforcement learning. So there have been two popular ways to build intelligent agents to solve sequential decision tasks. One way is reinforcement learning-based approach. An IL agent learns to solve a task by interacting with the environment and learning from the collected experience. It doesn't rely a lot on external knowledge, but the problem is the learning is usually pretty slow and it has very high sample complexity. On the other hand, symbolic planning-based approach doesn't have the high sample complexity concern because it leverages available human knowledge in the form of symbolic domain and action models. But its problem is it can be hard to capture all the details of the task using symbolic terms, so the model can sometimes be imprecise. To overcome the cold start or high sample complexity problem of RL, people have made some attempts to integrate symbolic planning into RL, to equip RL with human knowledge, and they have achieved very impressive results in some challenging long horizon tasks. However, most prior works are based on the assumption that the given symbolic model are precise. But this is an over-optimistic assumption because human-provided symbolic models are usually incomplete and imprecise. So in this work, we aim to address the problem of how to leverage an approximate symbolic model for reinforcement learning. Firstly, in our work, we introduce a normative concept called minimally viable task representation, or MVTR. It's used to quantify the conditions under which our approach can extract the correct task hierarchy information from the symbolic model. And then we show that by extracting landmarks as subgoals from an MVTR model, we can effectively overcome the imprecision of the model. Lastly, we show that by learning diverse set of skills for each subgoal, we can effectively overcome the incompleteness of the symbolic model. Starting from this slide, I will give some examples of approximate symbolic models. I will be using the household environment as the example, which is shown in the right figure. The task of the household robot is to get something on the shelf. To solve this task, the robot needs to pick up the blue key, go to the charging station to recharge itself, and then open the door and go to the shelf. Here, a human may misspecify an action model that aims to achieve at final room and door ajar at the same time. However, once the robot enters the room, that is, at final room become true, the door will become closed. This makes the symbolic action pass through door unexecutable in reality. Also, the human may have forgotten to mention the fact that there are multiple keys in the house, and only one of them can open the door. They may have incorrectly specified that the robot can use any of the keys. In this case, the symbolic model only partially specifies the prerequisite for opening the door. Moreover, the human can be unaware that this robot has limited battery capacity and sometimes needs to recharge itself at the blue charging dock. To accommodate these possible human mistakes, MVTR is designed to characterize a much more relaxed condition under which there is still a guarantee that we can extract useful task-relevant information from an imperfect symbolic model. Its formal definition can be found in the paper, and in short, it only requires at least one plan for the symbolic model to capture the right relative orderings of action effects. Then in the paper, we prove that, given an MVTR model, fact landmarks and their relative ordering are guaranteed to hold in the underlying task. So we use landmarks as subgoals, and the RL agent is supposed to find a policy to achieve each subgoal. Note that using landmark as subgoals doesn't address the incompleteness problem. To this end, instead of learning one single policy to achieve each subgoal, we learn a diverse set of skills. For example, when the human doesn't specify which key is the right key, we learn 3 different skills to pick up the 3 different keys. In the paper, we show that this can be achieved by using an information theoretic objective. For experimental evaluation, we use the three different environments, and multiple inexact symbolic models are given to the IO agent. Results show that our approach manages to efficiently solve all the tasks. We encourage the audience to check out our paper for more details. Thanks for listening.